Okay, welcome back to the information visualization lecture. Last week we covered a bit of history and the very basics of information visualization. Today's input is all about the visual perceptual system, which is really the foundation of any visualization experience, because of course we rely on our eyes and everything that's connected between the eyes and the brain. And for this, I think it's good to know that this is the eye and the connections to the brain form a very sophisticated organ. It is it's very fast, actually processing large amounts of data in the visual scene. It's actually the sensory channel with the highest bandwidth compared to the other senses. So it allows us actually to perceive all kinds of visual features. Here we have the visual variables again that we talked about last week, plus actually also the idea of perceiving relations among objects. So we see arrangements or configurations of objects, and this is all possible to be perceived and grasped very quickly. So I think we should actually start this lecture with a big applause for our eyes, for what's actually doing for our sense making in the world. So let's take a closer look at the eye. So here we have the main elements. So the iris, which regulates the amount of light entering the eye. It actually changes the size of the pupil, which is the dark circle, this circular opening in the center of the iris of the eye. Then we have the cornea, which actually provides a bit of light refraction. But it actually has a fixed focus, so it actually helps to kind of bring the light together. The lens itself is an elastic body that is used then to adjust the focus. So with the closing or the changing size of the pupil, also the lens actually changes its size, and the eye then is actually filled with a clear liquid, which is called the vitreous gel. And this is largely containing water, and it's actually the main responsibility is to maintain the spherical shape of the eye. And now towards the back of the eye is really where the interesting action is happening with regards to actually sensing and perceiving the different information in the visual field. So the optic nerve is actually the part that transmits visual information to the brain. The macula is the area which forms the center of the retina and is actually specialized for high acuity vision. So this is where we have the highest resolution, the highest detail in our visual perception. And this is also where we have the highest density of cones. We will get to this in a second. And of course, more generally, the retina, which forms the entire back, it actually covers the entire back side of the eye, is the light sensitive layer that contains all the photoreceptors that we're going to look at next. So photoreception is what turns light into visual information. This is also called visual phototransduction, which basically turns the electromagnetic radiation of light into electrical signals that can then be further transmitted and processed by our brain. And before it actually gets to the brain, we actually have that relatively sophisticated network of cells, of photoreceptors and processing cells that you see here on this slide, that already do some kind of image processing, actually, some kind of biological image processing. So actually there's some edge sharpening and some contrasts are being increased so that we can actually see and perceive shapes and so forth. And then these different signals, this different information is aggregated and sent to the brain via the optic nerve. Now, at the very top here, we see the different photoreceptors. The photoreceptors are kind of the first encounter with, or the first level of actually photoreception and of that process. And they basically turn light into signal, so that we will end up with a mental sensation of the world. And there are two types of photoreceptors. On the one hand, we have the rods, which are actually much more numerous. They are distributed around the retina. Actually, not so much in the fovea, so not so much actually in the focus area. They are actually only able to recognize gray values or brightness, let's say. And they have a response to a stimulus within about 300 milliseconds, which is a bit slower than the other type we're going to look at in a second. They are light sensitive, so they actually allow us to see also in dark situations. So they're very well suited for night vision. On the other hand, there are the cones, which are actually much fewer. There are much fewer cones in the eye, and they are really specialized photoreceptors. So first of all, there are actually three kinds of cones that are responsible for three different bands of the visual spectrum, so that we can actually differentiate between millions of colors. And the cones are actually centered around the fovea, so they are really in the center of our focused attention. And and the cones are basically not working so well in dark settings. Now here you have that again, so you see basically how the rods and cones distribute. So if we have, if the angle 0 is at the fovea, at this kind of focus area, you see that the distribution of cones, which is basically the line under which the area is in this dark gray, we actually have most of the cones around there. And then the distribution of the rods, the other kind of photoreceptor, the grayscale photoreceptors, they are actually more in the periphery. So and just as a side note, where the optic nerve kind of binds the different signals together and sends to the brain, there's actually a tiny spot where we have blind spot, and you might have noticed this. There are actually some tricks where you can spot this. Our eyes, the photoreceptors and the signal processing happening behind the retina, they are actually filling in the information there. So we actually don't notice that there is a blind spot in our eyes. Now, I mentioned that we have the cones as the kind of specialized photoreceptors. They are specialized into three different types, each with a specific sensitivity along the light spectrum. So this is here suggested in this diagram. So you see that, for example, the blue cones have a particular sensitivity in the lower wavelength spectrum, while the green and red cones in the higher areas, in the higher wavelengths. And when the light actually reaches these different cones, depending on how the light is basically, what kind of light signal it is, what kind of color distribution it has, the different cones will fire differently with a different sensitivity towards these different colors, basically. And the rods are kind of right in the middle there. They don't really distinguish much between different colors. They are basically perceiving brightness as a whole. And from the specialization of cones and rods and how they're distributed on the retina, we will actually get different kind of sensations, different types of visions. So while the cones provide a high resolution color information in the focus area, the rods help us to see the entire scene and kind of see arrangements. And this photo that we see here would actually need to have almost like an additional filter, because actually the periphery would be, in terms of the information that's actually sensed, would almost be black and white. But because our eyes are actually filling in the blank, of course, we see the sky to continue in blue, of course. But the actual color differentiation is of not high resolution or of not high detail. So we can distinguish basically between the foveatic vision, so that's the high resolution detail that we can see in the small focus area, and we have peripheral vision, which gives us orientation and kind of the larger overview of what is around us, basically. And then through quick eye movements that are called saccadic eye movements, we can change the focus, and we gradually, but actually quickly, build up a scene. We build up a sense of actually seeing everything at once. And of course, also through our head movements, we are able to then kind of construct and perceive an entire scene, even though at a time, at a given instant, we can only see we only see one focus area in sharp detail. Now, generally speaking, we can say that our visual system supports relative perception, so that perception depends on the spatial and temporal context of what we're seeing. So what we have seen before, or what we're seeing at the same time in the visual periphery, has an impact on what we actually can observe and what we can detect. So I will now show you briefly a few effects of this kind of perception, of this relativity. I will not go into the specific details of each example, but I want you to look closely now. And ideally, when you have the video open, you might want to actually put it on full screen now, so that you can see the effect of these different, that you can actually see these different effects. So first of all, if you now take a close look and focus on any dot and then move your eye around, you will see that some of these white dots at these intersections actually turn into black dots, right? So there's basically an effect that is through the contextual perception that we have, which is called lateral inhibition, that certain visual features in the immediate visual context will be perceived differently. And of course, that's a constructed example, but it kind of makes this particular arrangement quite unstable. Another example is called successive contrast. So if you now look closely at these two circles, spend a few seconds on this, let this kind of sink in. And then if we move to another set of circles that actually have the same color, they will actually be, you will actually perceive these two, identical shades of yellow first in very different colors. I will repeat this just to give you a chance to really see this. So here we have orange and green. And then if we have that kind of sink in on our retina, this will actually have a longer impact on the perception of these yellow tones. So that's successive contrast. There's also simultaneous contrast. So when we have a certain background or a certain contextual color or brightness, it might actually impact the perception of the color in the focus area, or not might, but it actually will impact that. So here, what you might not have guessed is that the gray areas in the middle on the left and right, actually have the same gray tone. but you perceive the right one to be darker than the left one because of the immediate context. Here we have the March bands, so they actually look like solid gray tones here when they're separated, but when we actually move them closer together without these separating gaps, you automatically you will have a very different perception of actually these gray tones, because now you might have you most likely will have a sense that these particular gray bands become brighter towards the bottom of each of these narrow rectangles. So let's go once more back. So in this case, these I think 8 gray tones seem like solid colors, no gradients. But when we're moving them together and we see basically the differences at these edges between them, our eyes actually increase the contrast between these tones of gray. And because of this contrast increase, we will actually perceive like little gradients there. Now, there are many other examples. This is just a quick set of effects to emphasize that our perception is relative. And we should have that on our radar when we're designing information visualizations, when we're using and maybe also seeing information visualizations. So our eyes see color in differences and not in absolutes. So differences to what we've seen before or differences to what we're seeing at the same time. Our human eye is not an accurate photometer. It's not a scientific instrument. And that's actually true to many sensory systems, that it's actually based on kind of relative perception. And to avoid problems in the use of information visualizations, we need to design with the relativity of visual perception in mind. Okay, so this is kind of the first maybe takeaway here from this lecture today. Now let's take a closer look at color. Let's get to what we have already talked about with regards to the photoreceptors. Color can be defined as the property possessed by an object of producing different sensations on the eye as a result of the way it reflects or emits light. This is the first definition of color in the dictionary. But there are different concepts of color depending on from which angle you actually look at it. So, color can be seen as the physical light, as perceptual impressions, as mental models, particular emotional associations. We have different cultural conventions of color, and there are, of course, also technical methods used to create specific impressions. Now, let's actually start from the technical end. There have been actually quite a few color models with which to mathematically represent color information. And let's pick maybe 3 particular important ones out here. So first, RGB is an additive color system, which is really based on the idea of cones being triggered in the retina by different segments of the light spectrum. We just talked about this, the red, green, and blue cones. There are few problems actually with using RGB, and maybe for us, particularly for the design of information visualizations, it's a highly technical way of thinking of color. It's not really intuitive, and it's also not so easy to actually talk or kind of communicate with color or with these RGB values. However, of course, this is a typical way also to define it in, for example, in HTML or CSS. You can also use RGB to define colors in Altair. This is a often used way of specifying colors. This kind of like the sister color model to RGB is CMYK, which is a subtractive color system, that is used for printing. It's basically the flip side to RGB, and we have actually similar problems that we just encountered with regards to RGB. Now, there's a family of color systems that are more centered around intuitive understandings of color. So this is neither additive nor subtractive, but they actually try to use something like hue, saturation, and lightness or brightness. There's HSL and HSB. So here we have the HSL color model, and it basically takes three values. So the first value, the hue, is actually degrees that go from 0 to 360. And then the saturation and lightness values are going between 0 and 100% to indicate the color purity and the level of brightness. That was actually also originally invented for television, so that the color information could be added to the existing black and white signal. But for us here, it's really useful because it's particularly oriented towards our understanding, our kind of everyday understanding of human vision. And it can also be defined in CSS as well as in Altair, which also takes these kind of CSS color definitions. Okay, now when you want to design with color, so actually use color in information visualizations, there are a few main uses. So first, we can group similar elements together. We can indicate measurements or quantities. We can actually represent color as it is used in reality. So if there are objects that have a color in themselves, we can actually use that color. We can use color to enliven or decorate, and also highlight specific items. So that's kind of the main uses. I will show a few examples now. So to maybe start with the highlighting. So we can actually emphasize, use color to emphasize elements. So here, if I asked you, spot all the sevens in this arrangement of numbers, you will have a hard time with just using this. But if we highlight them, we can actually spot them very quickly. We'll get to that in a second again, what kind of effect this actually is. We can also group rows or columns or different kind of sets of data items through these backgrounds highlighted in yellow here. As I said, we can measure, so we can actually use color scales to encode quantitative data. So here we have an example that is actually not a good example. It's infamous for being perceptually nonlinear. So the rainbow color scale is still often used, especially in certain scientific domains. But the problem is, you see right below, if you have a color deficiency in your perception, which actually quite a few people have, it will be difficult to actually see that linear order of data progressing. There are alternatives. So if you combine hue with value variation, you can actually avoid that non-linearity and arrive at a better color scale. Just to show you what the bad rainbow color map does to, in this case, a choropleth map of the United States, you will see, if you scan the different counties, that it actually will be hard, especially when quite drastic value changes are bordering each other, to make sense of where are the high values, where are the low values, and so forth. Instead, you should use again a perceptually linear color scale. So here on this site, colorbrewer2.org, you can actually pick and find color schemes. Here you see that both hue, so we are here going from yellow to blue, as well as brightness. So the yellow tone is very bright towards the blue that is going towards the dark blue. As I said already, there are different forms of color blindness. So the inability or impediment in perceiving the full spectrum of color. The different classes, which I'm not going to go into here, but it's important to know that actually 8% of men have some form of color blindness, in this case red-green blindness. However, while they may not easily distinguish red and green, most, like the very large majority, almost 100%, can actually perceive brightness differences. So it's important for you to check the monochrome version of your visualization. And actually, you can do this easily by taking a screenshot and taking the saturation away, or you can also start designing first without color and later on maybe adding some colors for highlights. So the different tactics. But for in terms of actually designing information visualizations, here are a few guidelines. First of all, when you're trying to visualize different categories using colors, it will be difficult to perceive the different categories or to identify them once you kind of go beyond, I don't know, 7, 8, 9 colors. Once you have more than 10, it will be really hard to, there will be some colors quite close and it will raise some confusions. We talked about the perceptually linear encoding, so you should choose a color scale that satisfies this requirement, especially with high saturations and contrasts. You want to be careful because as we talked about the relativity of perception, these high contrasts and saturations will impact our perception and might make it harder actually to see nuances and subtle differences. Of course, we should also be aware of cultural conventions, so certain colors actually signal something specifically. And in general, actually, I would say color is actually a rare resource. It's a kind of a precious resource that you should use purposefully and ideally only for one purpose. So use it consistently so that people do not get confused about it. Now that was it for now on color. Let's move further into element detection. So our eyes are really trained to pick up elements that stick out, and that again, color is always there. That can be, for example, because of their distinct color. So here, unless you have a red-green color deficiency, you would easily pick out or recognize the red circle. Of course, elements can also stick out by different levels of brightness. So this will be also working without having, even if there are color deficiencies in your perception. So brightness is a very strong way to kind of detect elements. We can vary orientation to spot elements. In this case, there's one slightly angled towards the left. The curvature can change. Here we have only one element with a straight line and it immediately pops out. We can have different shapes, different lengths, different sizes. So here's one element significantly larger, different enclosures. So you see there's one deviation and you will spot it immediately. Different convexities. So there's one element that is kind of turned the other way, basically. You can add additional elements and that will pop out. And now this might not be so quickly to spot. You have to look a bit more carefully, but if things are not actually connected or follow a different kind of angle to each other. And that's the question now. We will have a hard time to actually pick or spot the elements. For example, if I ask you here to, I don't know, spot all the red squares, it's a bit more complicated because we are now combining different visual features. And so there will actually not be pre-attentively processed, and that's what I wanted to get at with these example. Pre-attentive processing is a special form of perception with which we can quickly spot elements in relatively complex arrangements. So most of the early examples that you've just shown, that you've just seen, actually operate with pre-attentive processing, where you glance over it and within a very short time you will spot the element or the few elements that deviate from the visual features from the rest of the elements. The pre-attentive processing really favors visually salient, so distinct, as well as newly displayed elements. So there's a kind of a preference towards saliency and novelty. This actually operates across the entire visual field in parallel, so that's why it's also so quick. By knowing about this, and there are quite a few studies on this, the question is it actually entirely pre-attentive, or is there actually some focus? This might actually work quicker on the elements that are actually in the focus area, but generally speaking, this effect is quite powerful, and we can design towards this. So if there are certain tasks that you want to support, that you want to accelerate, that you want to support your readers to actually pick out certain elements, you want to design them in such a way so it can be perceived pre-attentively. And so this effect, or this mechanism, is really about detecting individual elements, but what about the perception of arrangements of multiple elements? And for this, the Gestalt laws or Gestalt theory actually provides robust rules that describe the way we see visual patterns, so the way we group elements together. Now let's take a look at a few of these robust rules that might also come in handy when creating information visualization. So the first, proximity. So here the spatial proximity becomes a powerful cue for the perceptual organization of this matrix of dots. So while on the left side the dots are perceived as rows, as horizontal rows, on the right side they are perceived as columns, and that is just due to the fact that they are slightly closer to each other, to the horizontal neighbors on the left side and to the vertical neighbors on the right side. Right, a very simple effect, but something you can actually work with. So here we have 9 squares arranged in distinct ways. So on the left, they are placed in low proximity, so they are kind of scattered, and in this way they are really perceived as separate shapes. On the right, the squares are placed in very high proximity, and in this case they are actually perceived as one shape. So here we are actually considering these elements as a whole and not as individuals. That also operates on the basic principle of proximity. We also see a similar effect through similarity. So here the similarity between the elements in these alternate rows causes actually this row percept, the impression of distinct rows to dominate, and in both cases actually. Another principle is the principle of connectedness. This is also a powerful grouping principle that actually is stronger than proximity, as you can see under A. It can also be stronger than color in the case of B, as well as size and shape, as you see on the bottom. So connectedness, which is something that can be used especially when we're looking at network representations, is a strong grouping principle that lets us, of course, see elements to be in some kind of connected grouping to each other. Another principle is is continuity. So here we see a pattern on the left, which is you probably see a curve overlaid on top of a rectangle, and we perceive that curved line to be in a way its own entity on top of the rectangle, which is kind of the interpretation that we see in B, instead of kind of the interpretation that is indicated in C, where the two shapes are actually kind of counterintuitive, because our eyes actually favor, and through this also kind of expect continuous curves and lines, and not these kind of abrupt edges. And that actually also has an impact on how we perceive these connections. This will again be relevant in network visualizations especially, but also in diagrams in general. The smooth, continuous curves on the left are for us easier to perceive than these abrupt changes in direction on the right. So it's much easier for us to spot which elements are connected on the left than to really kind of follow these edgy connections on the right. There's also the principle of symmetry. So here we have different patterns of kind of visual shapes. So on the left, we see two identical parallel contours, and in the middle and on the right, these identical contours are reflected about a vertical axis, and these kinds of symmetries that we see in the middle and on the right arguably result in a stronger sense of a holistic figure, of some kind of holistic appearance, and makes it easier and maybe more approachable to perceive. Now, a bit related to continuity and kind of how our eyes favors certain objects is the principle of closure. So closure holds that our neural mechanisms that we talked about earlier really operate to find kind of closed contours and in a way kind of intact objects. Of course, we have trained our eyes in the physical environment. So here we are kind of filling in the blank. On the left side, we would expect that the circle actually, or this 3/4 of a circle actually continues as an entire circle behind the green rectangle, and that we're not actually expecting the circle to be broken as indicated on the right side. So we are kind of filling in the blanks, and that's something we do subconsciously without actually thinking about it. And then the last principle that I wanted to mention here from the Gestalt theory is the idea of figure-ground organization, so that that we recognize that our eyes, our perception interprets scenes as a form of foreground and background, and that this actually this relationship actually structures our perception and in a way also orientation in a visual scene. So here we have the Dutch artist M.C. Escher playing with this figure ground principle, with our perceptual need to separate foreground and background. And as you can see in this artwork, the fish and birds become the figure in front of the background formed by the respective other. So the fish on the bottom, as you kind of move slightly up with your eyes, you see that the black background between the fish become the birds, which then, where their background, especially around the horizon line, you see that you see basically these two shapes at the same time. The white fish, or the bright fish shapes, dissolve themselves into the background, right? Okay, so now all of this can be summarized with a few rules of thumb for the design and also interpretation of information visualizations. So I think a really good rule of thumb is get it right in black and white. When you're creating visualizations and you're using color, it should still work, even if people may not perceive the exact hue. So for that matter, also the principle of not doing harm, so only using color and contrasts sparingly, to actually optimize for brightness and not hue, to limit the color palette and be selective when you're using them for categories, and also to, as I said, to avoid high contrast and saturation. We briefly talked about the effects of pre-attentive processing and how elements can pop out and can make it really easy and fast to detect elements, and therefore also as a next step the arrangements. So you can be strategic about this by selectively using visual variables that support that. And we briefly talked about the Gestalt theory, and which helps us to think about the design of towards proximity. Actually, we just looked at the distinction between background and foreground. To design connections that are continuous and therefore easier to be perceived, and to think about how the elements can be designed so that they can be perceived as arrangement or as groups, in case that is actually what the data contains. Now this is it for now, for today, for the perception lecture. We have, of course, another assignment. So until next week, I'm asking you to closely examine an information visualization and briefly answer questions about the data set, encoding, and interaction. So this is an assignment in which you really kind of sharpen your critical eye. So I'm asking you to explore what are the items and attributes in the underlying data, how is the data mapped to visual marks, and which channels are used, and what are the interactive capabilities of the visualization, if there are any. I'm asking you to post your analysis with short descriptions for each point by next week, Wednesday, by 22nd April. And please leave a link to the visualization that you have considered for that assignment. So thank you very much, and talk to you later.